This is 1.5.1 and 1.5.3 A and C. So they're both the same question. Okay, and so we can answer them in one video. So 2 cards are chosen from a pack of cards without replacement. And we want to calculate these probabilities. So A says both are picture cards. So we're looking for the probability that the first is a picture. And you have to have the second one be a picture. Right? That's what has to happen and get 2 picture cards. So anytime you're looking for the probability of an intersection like that, you need to use a multiplication rule. But what you have to ask yourself is, are these 2 events independent or dependent? Because depending on what you answer, that's going to affect which rule we use. So you have to ask yourself, is the event getting the first card to be a picture card and the second card to be a picture card, are those going to be affecting each other in any way? Are they independent or dependent? So if you look at it, the first picture card and second picture card, there are only, 12 picture cards in a deck, right? 3 from each suit. So if there's only 12 picture cards in a deck, and I take one out for my first card and I don't put it back. So without replacement means we're not going to put it back. So if I don't put it back, now the next time I go and draw a card, there's only going to be 11 picture cards in that deck because there's less picture cards to choose from. So you don't actually have to do huge complicated proofs. You just have to ask yourself logically, if I take out one picture card, will that change the possibilities or the chances of me getting another picture card? Yes, they will affect each other. So in this case, they affect each other. So that means they are dependent, which means we're going to need to use the general multiplication rule. Now you'll notice I don't usually write this out every time when I'm doing simple probabilities like this because I can just kind of do it in my head. But if you want to write it out, remember the general multiplication rule says the probability of A and B is equal to the probability of A times the probability of B if you know that A already happens. So basically it's saying you can't just do probability of A times probability of B because B is affected by A happening. So in this case, we said the probability of that second picture card is going to be affected by the first card being a picture card. So in our case, we're going to need the probability of the first picture, and we'll use that intersection sign, and the second picture is going to be equal to the probability of the first being a picture times the probability that the second one is a picture if you know that the first one is a picture. So now we ask ourselves, what's the probability of getting your first card to be a picture card? Well, again, there are 4 suits. Each one has 3 picture cards. So that means there are 12 picture cards out of 52. Okay. Now we're asking, what's the probability that the second one's a picture card if you know the first one's a picture card? So that says, I already know I took out 1 picture card. So that means if I want to get another picture card, there are only 11 picture cards left out of a total of 51 cards. Because we took out 1 card and we didn't put it back, so there are less cards to choose from. So that's the probability that both are picture cards. Okay. And for 1.5.3a, we've decided that they were dependent because they're affecting each other. Again, on 1.5.3, I told you don't try and do the proof. Just think about logically. Yes, they're going to affect each other. They are dependent. B, let's find the probability that they're both red. So our probability that they're both red is going to be equal to the probability that the first is red and the second is red. So now you have to ask yourself, okay, what multiplication rule do I need? Are these going to be affecting each other? Well, if you think about red, there are 26 red cards in a deck. If I pull one out and I don't put it back, now there's only going to be 25 red cards in a deck. So every time I take out a red card, there's less red cards for me to choose from, so it's changing the probability. So they're going to affect each other. Sorry, I'm trying a new pen. It's not working. Which means that they are dependent. Now this is 1.5.3c. All you have to do, you don't have to try and prove it, you just have to say, okay, when I take out a red card and I don't put it back, because again it's without replacement, that's going to change my probabilities, so they're dependent. So I need to use the general multiplication rule. Now remember, the difference between the general multiplication rule and the multiplication rule for independent events is just that it simplifies. So you could always use the general multiplication rule every time. So let me show you. So the probability of A and B is equal to the probability of A times the probability of B given A. So this is our general form that works for every situation. But if A and B happen to be dependent, then A doesn't affect B. So this would just simplify to the probability of B, and you wouldn't have to worry about the given A, because knowing that A happened doesn't change the probability of B. So that rule simplifies. But if you can't remember them, just use the general multiplication rule every time. So now, for our problem, we're looking for the probability that the first is red and the second is red. We're going to use that general multiplication rule, so we're going to do the probability that the first is red and the second is red. Sorry, I'm just writing the wrong thing here. Probability that the first is red times the probability that the second is red if you know that the first is red. Okay, let's see. So what's this going to mean? Probably the first is red. I think we said half the cards on the deck are red. So there are 26 out of 52 cards that are red times, now the probability the second is red if you know the first one's already red. So that means we already took out one red, so there's only 25 reds left out of a total of 51 cards. Now you'll notice most of the time I'm not going to bother writing this out if it's simple problems. Okay, I just write the 26 over 52 times 25 over 1, because I remember in my head every time I do this multiplication to always think, how did it affect me? Did I take out a card? Do I have to change the probabilities because I took out a card? And so I just kind of do that part in my head. And part C. We're looking for the probability that one is red and one is black. So we want one red and one black. This one is different because it doesn't tell us which order. And you always have to be paying attention to this to see what order. It's like up above it said do red and then red. Here it doesn't say what order. All it wants is at the end. It wants one red and one black. So you can make a probability tree. You can say the first card could be red or black. And then the second card could be red or black, red or black. So our possible outcomes are going to be red, red. So if I put it in a sample space there, red, black, black, red, or black, black. Now when we write this, this is always assuming that this is red and red, red and black, etc. We just don't usually write that because it takes more space to write. Now that we've figured out what our outcomes are, we need to ask ourselves which of these outcomes will give us what we want. So we want one red and one black. That means I could get red, black, that would give me what I want, or I could get black, red. Notice two reds won't give me what I want, two blacks won't give me what I want. But it could be red and black or black and red. So we write this out. So we really want the probability of red, black, or black, red. When you have an or, that means we're going to need to add it. So probability of red, black, plus the probability of black, red. Now technically you should probably minus out the probability of the intersection. Red, black, and black, red. But these are disjoint events. They can't both happen at the same time. You can't get red and black and black then red at the same time. This is a sequence. So it has to be one or the other. They're disjoint, or mutually exclusive. So you don't have to worry about that. That's just a 0. Anytime you're doing tree diagrams like this, they're going to be mutually exclusive. You're not going to have to worry about minusing out the intersection because you can't have both things at the same time. Okay, so we want red, black, and then we also need to find the probability of black, red. We're going to find those separately and add them together. Now, I could write out that general multiplication rule again, or I can just do it in my head. So when here, I'm looking for the probability of red and black, and then separately we'll find the probability of black and red. Now when I write out like this, the sequence is implied, so I know I'm doing red first, so I want to get a red card first. There are 26 red cards out of 52 total. Times, now I want a black, but I know I already got a red first. Well, if I got a red first, that means I didn't touch my blacks, so there are actually still 26 blacks, but there are only 51 cards because I took a card out. Okay, plus, now I need to do the probability of black first. So black would be 26 out of 52 because I've started completely over because this was an OR. So everything over here doesn't affect it at all. Okay. Let's see, so I did black first, and now I want the probability of red if I know the first one was black. So if I know the first one was black, that means that there wasn't a red, so there's still 26 red, and there's only 51 cards because I already pulled out a black one. And that would be your answer here.